Okay, just looking at this tentative list of things that I thought this morning I'd want to put on the exam, and some of these are just incomplete notes because these were intended for me, not you, but I printed it off anyway. Okay? Not that I don't want you to know, it's just that I didn't try to make it clear so you could read it. Okay, if you subdivide a partition, then the area, corresponding area under the curve approaches the area of the under the curve. But there are ways of subdividing a partition. Let's say here's my original intervals from here to here, right? So here's a partition. Here's an interval, right? Okay? Okay, I'm going to do a partition where the mesh doesn't approach 0. Here's a perfectly good partition. You ready? Okay. Now, what we did before, we more or less cut each interval in half, right? But I'm going to do this. Then I'm going to cut these in half. Then I'm going to cut these in half. Then I'm going to cut these in half. And I'm going to keep cutting these in half.
We haven't learned about meshes, have we yet?
Well, I haven't touched this interval or this interval, right? So we still have a potential big gap between the trapezoidal approximation and the curve, right? On this interval and this interval, it's not changing. But I'm still refining the partition, right? Okay? Now, one way to make sure I could do this, okay? Then I could cut this one in half and cut this one in half, cut this one in half, cut this one here. Then I could cut this one and 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 this one. And then I could just start cutting them all in half, right? I'm not cutting them evenly, but maybe there's a reason I cut it this way. And then start halving each interval, and that would imply that the mesh approaches 0. Now you might not know what a mesh is, like, you know, it's like a screen, and if you got gravel or something, you drop it on the screen and the fine particles go through and the bigger particles, you throw them away because you're trying to, you know, or sifting flour, okay? You can use a mesh. And the mesh is the size of the biggest thing that can go through, okay? If the mesh goes to 0, that means every time it gets finer and finer and eventually approaches 0, okay? And if you're talking about doing a mesh for these intervals, you know, it's not two-dimensional, so it doesn't quite work with a screen, but it just means the biggest interval, whatever the biggest interval is on each on the partitions, gets smaller and smaller and approaches 0. That's the mesh. That just means you have some maximum size in the interval each time you refine the partition, okay? And that maximum size approaches 0. Then, if your function isn't pathological in some way, and we can write pathological functions easily, but most of the functions that we use in applied stuff aren't pathological, and for most of the functions, all the ones we're studying, the area of the trapezoidal approximation will approach the actual area under the curve as a limit. Okay? So that's what we mean by mesh, and that's something we talked about yesterday, and you kind of recognize that. And then I say, what are the specific meanings of these terms? Because I knew I hadn't told you what mesh is, right? Just reminding myself to be specific about the terms. Okay. Now, a function is increasing or and decreasing. How can a function be increasing and decreasing? Well, I know what I meant by that, and I didn't write this for you, but I'm showing it to you. It means you got a function. Okay, if a function is always increasing, that just means the function can go up and down and up and down. It can do this, okay? And we can certainly say that this applies if the function is increasing, but it's a little harder to say it if the function's increasing and decreasing, and we'll probably talk about that. Okay, and if I was stating that as a problem, I'd give you an example of how it could be increasing on some intervals and decreasing on others. Bug population. Problem on your homework. I'm just going to do 3 trees. I'm going to say there are 100 on this one, 500 on this one, and 300 on this one. And this is like the saying demented. Every tree is going to lose 10% of its bugs to each of its neighbors. Of course, there's only one tree that has more than one neighbor, right? They're in a line, yes.
So does the middle one give 5% to the both of them?
Is the middle one what?
Give 5% to that one and 5% to that one?
No, 10% to each. Now, that's the statement, but you don't have the statement. I mean, you do, but you know.
What? No, it's not.
Huh?
It doesn't give 10% to each. Each of them loses 10%.
Okay, each tree loses 10% to each of its neighbors.
Yes.
Okay, which means each tree gains 10% of whatever's on its neighbors, right? Okay, so I'm not sure what I said, but those are equivalent. Okay, so what you have is 10% to each neighbor, so 10% of 100 is 10 bugs, right? And this tree only has one neighbor. And here, we've got 30 bugs. And then from this tree, you have 50 that go this way and 50 that go this way, right? Okay? So you can easily figure out that the next transition, you're going to have, let's see, you're going to lose 100 here, you're going to gain 40. So you're going to lose 60, you're going to have 440. This one's going to gain 20, it's going to be 320. This one's going to lose 40, now gain 40, so it's going to be 140. And then you can do it again, right?
I have a question.
Simple model. Much like the same demented, but you got 3 trees and they don't all act exactly the same because they have different number of neighbors. Yeah.
Can I come up there and kind of show you my question?
Come on.
All right. If this loses 10%, this loses 10%, this loses 10%.
To each neighbor.
To each neighbor.
Yeah, go on.
Oh, so these would not be 25 each? Because on the homework, I did my 3x3 matrix and it only worked if 50% went here. No, sorry, 5% of the 10% lost went here and 5% went here.
But that says 10% lost to each. Now, if you worked it that way, it's a different problem, but it's still a good problem, so it's not bad. But that ignored the word each. You understand? When I say it goes to each neighbor?
Yeah.
And don't worry about it. If you did that right, I'm happy. Okay? But make sure you pick up the word each. Okay? Okay. So you've got that model. Actually, I did assign that yesterday. I was thinking that was for today.
You're giving it to us again today?
I don't know. Right now, I want to just kind of get through these. And so probably I didn't assign for today if I did yesterday. I'll check that out when I do the thing. Okay. Okay, now, what I mean by the next one, the rate at which the velocity of a pendulum changes is proportional to how far it is from its equilibrium position. What do I mean by directly proportional to?
Like exponential? Or
1 to 1.
Huh?
1 to 1.
What do I mean by proportional to the square? Just testing to see if you've ever seen it. Okay? Yesterday we did a problem where the rate of change was proportional to the square root of y, right? We had, okay, just to use this example because we saw this, y prime equals k square root of y, right? Okay? That says
Isn't directly proportional you multiply and inversely proportional means they're divided?
you're talking about direct and inverse proportion? Yeah. If I said inversely proportional to the square root of y, then it would be k over the square root of y, right? Okay, and that's good, because you've seen direct and inverse proportion, which is a good place to start. Okay? But you might not have seen this formula. Okay? So this could be interpreted this way. I'll say A is directly proportional to B means there exists a constant number k such that A equals k times B. Okay? Among other things, if one of these is 0, the other is 0. So a graph of A versus B would be a line through the origin with a slope of k. Now, I'm not going to work that out, but we'll talk about it a little more. Okay? So this means if we know that the pendulum, now I'd have to say it, we don't have time to write it, so I'm not going to say much more about it, but you want to kind of digest that idea. Then we'll build on it, okay? And if it was inversely proportional, it would be k divided by b. Meaning if b goes up, a goes down. Here, if b goes up, a goes up at rate k, okay? Rate of change of A with respect to B is k in this case. And then I said if the altitude of a graph rectangle, I don't say any more. Obviously that has no meaning until I do. And there's another proportionality thing there. Now on the next one, I say the area under the graph can be approximated by the number of selected rectangles in a grid as the diagonal of the grid approaches 0. What do I mean by that? Well, I mean, we'll do it in a little box here. Okay, I've got a graph that extends from here to here. Okay? I can make a grid. And if I know the area of each square, or each rectangle, I can count them and figure out the area under the curve, right? Now, I'm not going to figure it out exactly, so I could count all the squares that are completely under the curve, or rectangles. I could count all the rectangles that touch the curve but are above it, that are partially above it. So I count all the rectangles completely below and all the rectangles partially above. I get an overestimate of the area and an underestimate of the area. Is that clear? Now, what if I subdivide these, like refining a partition? What if I refine the grid, make all the rectangles smaller? Then there's going to be less difference between the two estimates, the overestimate and the underestimate. And the smaller I make these squares, the closer my estimate of the area, or the less difference there's going to be between my estimates of the area. And my estimates of the area in the limit are going to squeeze the area between them. Okay? Because as the rectangles get tinier and tinier, if their areas approach 0, they're going to complete the squeezing, and you're going to get the upper estimate is going to approach the lower estimate, and that's going to be your area. Does that make sense? Have you seen that? Did you see that in your calculus course? In an applied calculus course. It's not a college transfer course. You probably wouldn't, even in a college transfer course, you probably wouldn't. In an engineering calculus, you should see it. Okay? Make sense?
Yeah.
Okay.
What's your quarterback?
Sorry?
What's your quarter?
Yeah, give me paid Manny.
Well, okay. Thank you.
You better stop your
I'm gonna. But I had to get my quarter.